if the sound quality doesn't fix itself or stays the same, guys, I apologize. But we're just gonna go ahead and see if we can just power through the stream, and hopefully there's no major issues with sound quality. All right. So, guys, today we're talking about the death of stars. Yeah, sorry about the Noel, but yeah, that doesn't seem like I could do much about it. I've tried to switch between the two mics I have here, and both are giving me the exact same issue. We can pretend it's a national press conference. Yeah, that's one way. Thank you. At least no buffering. But right, stellar death of stars, guys. So, whenever you think about the death of stars, we can think about one of two types of tracks that stars can take when dying. And this is heavily dependent upon, well, the mass of the star. But in general, when they first die, they kind of start off the same way. But before actually talking about their death, let's kind of talk about what life is like for a star, especially a main sequence star, while it's still on the main sequence. So, to talk about that, we need to talk about the fact that within main sequence stars, within their cores specifically, we have hydrogen fusion occurring. And this hydrogen fusion is what helps the star maintain its physical size and power output while it's on the main sequence. And this process in which the star is kind of in a stable state is known as hydrostatic equilibrium. And so what's occurring at this particular point in the main sequence star's lifetime, we have gravity constantly trying to push the star in, while we have that particular pressure acting on the gas. We have an opposite force or pressure occurring in the opposite direction. And these two pressures being the gas pressure from the particles themselves within the star, and the radiation pressure. This particular pressure is due to light being produced from nuclear fusion occurring within the star's core. And so there's this kind of struggle between gravity trying to collapse the star and the gas pressure along with the radiation pressure pushing outward to kind of stop that collapse. This whole process is known as hydrostatic equilibrium. It occurs in both what I'm going to term, or what's generally termed to be low mass as well as high mass stars. However, again, the reason why we're able to have this hydrostatic equilibrium is because of the fact that we have the gas pressure and the radiation pressure pushing outward. But what happens if we were to remove one of those two, specifically speaking about the radiation pressure, due to the fusion occurring within the star's core, specifically hydrogen to helium fusion? Once that's removed, this particular point in the star's lifetime is when the star is now beginning to what we call die. So once hydrogen to helium fusion stops, and we basically pretty much have a helium core, the star is now in the process of dying. It's now lost that radiation pressure, and it's going into a different phase of its existence. I really want to make sure that I'm not missing out on any sort of comments. So every now and then I'm going to go back and forth and check comments and see what's going on. All right. So the moment this happens for both a high mass main sequence star or a low mass main sequence star, the evolutionary track in which the star takes will differ. And like I said, this depends on the mass of the star. But in general, it kind of starts out the same. So what I'm going to primarily be talking about now are for low mass stars. And I'm going to define low mass stars as stars with stellar masses that are in the vicinity of 8 solar masses and below. So initially, we have the situation of we have a helium core. And in our image here, it's termed an inert helium core. So there's no sort of fusion or anything occurring within the core. Immediately on the outside of that, we're going to have a hydrogen shell for right now, and beyond that we have the rest of the star. So what happens now is, given that the radiation pressure from hydrogen to helium fusion has now stopped, gravity is going to start winning, and so the core begins to shrink. But this is the helium core, as well as the hydrogen shell around it, begin to shrink. And because of the fact that it's shrinking down, the temperature is going to be able to rise enough to the point where the hydrogen within that shell around the helium core can now also begin to fuse into helium. That fusion of that hydrogen shell, known as hydrogen burning, will now allow for radiation to be produced, and that radiation will produce a pressure on the outermost layers of the star, causing it to expand. Now, if you guys can remember from our very last stream, I kind of talked a little bit about Stefan Boltzmann's law, and the fact that there's this relationship between the luminosity of a star, its physical size, and its temperature. And this is specific to what will be the photospheric level of the star. And so what ends up happening is, as the star is expanding, the radiation that's coming from the hydrogen burning will produce more luminosity, and the physical size of the star is getting bigger as well. And so, sorry guys for a quick second, let me look at this really fast. All right. Are we still having any sort of issues, guys, with, I'm seeing buffering. Are we having buffering issues, guys? All right. So Larry, I see a quick question here. So hydrostatic equilibrium never matters. So yeah, hydrostatic equilibrium is typically a process is a process that occurs for spherical objects. All right, so moving on, we have this situation of the fact that we have that shell of hydrogen burning or being converted into helium, and the star itself has now expanded out. And as far as our solar system is concerned, the expansion of a star like the sun will engulf essentially definitely the inner two planets. It can actually grow as large as our orbit and probably take Earth with it. But eventually what ends up happening with the star is that the core of it will begin to shrink more and more and more over time, and eventually it will shrink down to the point where the pressure will build such that the temperature increases enough to the point where we'll have hydrogen-helium fusion. And so what will happen here is we'll have what's known as the triple alpha process. And so the helium will begin to fuse to produce higher elements, primarily producing carbon. And this is essentially how we end up with the carbon core of white dwarfs. And so, as we produce more and more carbon, we're getting the helium converted into carbon. In the case of a star like our own, the sun, what will end up happening is very similar to what I'm going to show you here in this video. All right. So the outermost layers of the star has expanded out. The core was contracting. Eventually, the core contracted enough till we saw what it looked like to be like a little small explosion, which for stars like our sun, and I believe this corresponds to stars that are somewhere around 2 solar masses or below. you'd have what's known as a helium flash, which is essentially the point at which you get the helium core compact enough to the point where the temperature is high enough for it to be a runaway helium chain reaction that is converting the helium into carbon, and you kind of get like this, like what it looked to be like a little explosion. But after all of that, you're kind of left with this planetary nebula, and at the very center of it, so at the very center of this image, or this animation that I'm showing here, we're left with a white dwarf. Now, the white dwarf itself is going to be composed primarily of carbon. However, there will also be I don't want to say trace amounts, but there will also be some amount of oxygen as well within these stellar objects. And so this is kind of the ultimate end for stars that are low mass. So again, low mass stars being 8 solar masses or lower. However, for much higher mass stars, the situation is a little bit different. For much higher mass stars, we again do still have the whole situation of having outermost having a hydrogen shell and a helium shell, where the helium shell eventually will burn to start producing carbon within the core. But for much higher mass main sequence stars that go into the process of dying, we can get a situation where we're producing much higher mass elements. Specifically, we can go from producing carbon within our core to producing elements all the way up to iron. And so at that point, once we've gotten to the point where we're producing iron in the core, we can't produce elements past iron. And because we can't produce elements past iron, there won't be any radiation pressure from the core, or there won't be enough radiation pressure to be able to stop the star from collapsing. And once the star collapses, and it implodes on itself, which is the collapse, and it explodes, and it produces what's known as a supernova. Now, in this particular case, with the death of high mass stars, these are supernova type 2. And out of the result of this supernova, we can end up with one of two types of stellar objects. And this again will depend upon the mass of the main sequence star that produced the supernova. If I'm remembering correctly, I think when you have masses above 8 solar masses, you are in the regime where you can begin to produce neutron stars. And once you make masses somewhere, I believe, above 20 solar masses, you can start to produce more compact objects, specifically a black hole. And so pretty much in a nutshell, that is the two different paths that main sequence stars will take as far as dying is concerned. Where at the end of this cycle, they will end up either being a white dwarf, which is in the case for low mass stars, or being a neutron star or a black hole, which would be the ending stellar objects for high mass main sequence stars. So I'm now quickly looking at the comments and want to see if I can work through them. I would say if I saw that. All right, so if a star that has extreme rotation, that has extreme flattening at the pole, will it still have hydrostatic equilibrium? I've actually never run across that question before. So what sort of stars exhibit the characteristics that you're describing here? Main sequence stars, that is. Okay, so Hanny, now that particular question, does a star get bigger from the hydrogen shell burning or the consequent helium core burning? So the star gets bigger from the hydrogen shell burning. And for that animation that I was showing earlier, typically stars that are in the red giant phase, I believe they're in that phase for roughly sometime around on the order of 1 billion years. A star with a companion. Hmm. So what sort of stars are we thinking about in this binary system? Typically, when I think of two stars, the stars would affect the dynamics of each other. But I thought you were kind of talking about intrinsic rotation, not so much orbital rotation. So just going back to Larry's question earlier, if a star that has extreme rotation, in this case I'm thinking about intrinsic rotation. But in the case of a binary star system, there would be that would affect the orbital revolution of the stars. Right, a single star, right. I honestly don't know the answer to that, Larry. I would have to look it up. But from my understanding, typically the situation will be that, or better yet, let's put it this way: hydrostatic equilibrium typically occurs for objects that are spherical. If the object becomes flattened in some sort of way, I don't want to say that hydrostatic equilibrium is not possible, but it's kind of hard for me to imagine how it would occur, because many of the diagrams I've seen exhibit hydrostatic equilibrium in cases where the object's spherical. So I've never actually really thought about the situation where it's flattened. Well, the thing about it is that it depends on what sort of star you're talking about. Um, di- Different types of stars will achieve hydrostatic equilibrium through different means. Main sequence stars will achieve it burning by fusing hydrogen in their cores. Um, in the case of giant stars, they attempt to achieve it by fusing higher elements within their cores. And in the case of, for example, white dwarfs and neutron stars, white dwarfs would achieve it by electron degeneracy pressure, fighting against gravitational collapse, and neutron stars will achieve it by neutron degeneracy pressure. Is there a prefix? Okay, for plasma rather than water? It could be. Um, I honestly don't know the reason why it's called hydrostatic equilibrium, but I think it's more so talking about a steady state of fluids. So yeah, hydrostatic apply for all fluids. Under high pressure, gases become fluid and then solid. I'm not too sure I understand that part. Yes, I'm aware of this. And honestly, I wasn't even aware that this particular concept, that is, hydrostatic equilibrium, was even used for solid objects. Um, the only time I had ever heard it used was in the case of stars. So yeah, gases are considered fluids to some extent, not by the strictest mean of it, but strictest means, but yeah, I really want to make sure I'm clear on that though. Gases are gases, but in general, whenever you're talking about a fluid or something that flows, you could think of like a gas flowing or a liquid flowing. So I don't want to say that gases are liquids. They're two different phases of matter, but I love our conversations. You guys always ask great questions. And I typically find myself after the stream like, I wonder what's up with that question. Couldn't agree with you more, Peter. Gases are gas. That's right. But yeah, today was kind of a short, a fairly short presentation for the depth of stars. So Henny is asking, I still want to know how the Earth-sized planet smothered Uranus interior. I'm gonna be honest with you, Hanny. I don't know what you're talking about here. Give me 1 second, because I'm curious now. Oh, was this brought up in one of the other conversations? One of the other CosmoQuest streams? Hmm. So I'm actually quickly looking this up. Axial tilt of Uranus. Yeah, you guys have definitely asked a question that I'm completely unable to answer or to even give any insight on. That is with the question about Uranus's axis tilt. Yeah, I definitely agree with you on that, DPI. Oh, that is weird. Honestly, guys, this is something I wasn't even aware of. So I'm now looking at an image that shows the tilt of the axis relative to the orbital plane of the object and of the planet, and wow, that is kind of insane. Yeah, I honestly don't know the answer to that, but I'm definitely gonna look it up now. Um, so what I'm talking about now is so someone asked a question earlier that I believe was related to the reason why Uranus is its axis of rotation, and the reason why its axis of rotation is at such a high angle relative to its orbital plane. I'm seeing an angle here of like 98 degrees, which is So if you were to go to Google and you were to type in, let's see, and you were to type in axial tilt of Uranus, and go to the images, there's an image here that shows all of the rotation axes of the planets and the angle those rotation axes are relative to their orbital plane. And it just so happens to be that in the case of Uranus, it's the angular separation between its orbital plane and its, or wait, I might be getting that wrong. Wait a second. Axial tilt relative to vertical. Sorry. So the angle isn't relative to the orbital plane. It's relative to, I guess, it will be perpendicular to the orbital plane. Well, guys, at this moment, I don't have any much more to say about the topic of today's discussion. So I think I'm gonna go ahead and end the stream, and we will be back next week with a different discussion. Yeah, guys, thanks for joining us today, and we will definitely see you guys next week. Yeah, DPI, of course you can ask questions. Go ahead. So, Joe, this is going to be primarily for you. This is a coding question. Duplicate. What are you referring to exactly? Are you referring to one of the mapper projects? Actually, yeah, I did. It was actually quite nice. Thanks for asking, Peter. I hope your holiday. Well, I hope everyone's well. It's the 4th of July. It's an American holiday, so I can imagine that some of you guys wouldn't celebrate it. Oh, no problem, DPI. I think the software for the mapper projects is designed such that you should not get duplicate images. But since you brought it up, I'll definitely ask about it. Oh, So the case could be that some of the images overlap one another, which could account for the reason why you're seeing the same craters. I'll have to check into that though. Yeah, exactly. The images overlap one another. Exactly what Noel is saying. Yeah, I would have to look at the images to see exactly how much they overlap. Oh, no sound? Joe, is your audio muted? Video's good. What's up with Joe's audio? Yeah, I can no longer hear you, Joe. Let's see. I haven't changed any of the audio settings on my laptop. All right, guys. So we're gonna go ahead and end the stream, and thank you guys for joining, and we'll definitely see you guys next week on Wednesday after Daily Space. All right, guys. Bye.